Hi, welcome everyone. Welcome to session 5 of the Intro to AI-Driven Science on Supercomputers. Today, we're going to have Taylor Childers back to talk about data handling for AI training. And we're also going to have a science talk from a postdoc here at Argonne, Ricardo Balin, who you've actually probably seen around answering questions in the Slack. So with that, I'm just going to hand things over to Taylor and we can get started.
Thank you, Paige. Hopefully get the right window here. Okay. So everyone, make sure, of course, that you ask your questions on Slack in the 05 data handling channel. So I'll be talking about pipelines today. We're going to use Jupyter Notebooks to start, and then we're going to hop on Theta GPU on the command line. So I'll review those as we go. And actually, maybe we should start with that. Let me change my share. We're going to start by review, login, and checkout. So let me switch to my terminal. Okay, so if I log into Theta, okay. Got my home directory here, which is probably quite a bit fuller than yours. I'm going to go into the AI for science training. And I'm going to do a git pull. Now, I'm on the master, and that just means that I'm not using the fork, and that's because I was committing content. If I do git remote-v, you can see I'm on the main here. If you've set up your fork properly, your origin would be listed as your GitHub username and then the AI series, and then you would also have the upstream or whatever you decided to name it. And in that case, you would do git fetch upstream and hit enter. Of course, that's not going to do anything for me. That's going to retrieve the latest data from the GitHub at the upstream location, which should be defined for you at this place. And then you're going to want to merge the content. So then you would do a git merge upstream main. And so that's going to merge the upstream main branch with your local repo. And so at that point, you should be up to date. And then, so once you have this checked out, we can move to Jupyter, because we're going to use there's a notebook down in the data pipelines directory that we're going to use. You can see right here. So now I'll go back to my browser. And we will start in the README file in the data pipeline just here on the website. So I'm going to use the code that Corey presented to you last week, which introduced a more modern network construction called ResNet. And he didn't talk at all about the data pipeline that he was using, and that was because we're going to talk about that this week. So, you know, when you're doing deep learning training, often you are, first of all, on a hybrid system like we have at ALCF on Theta GPU or Polaris, where the computer itself has CPUs and GPUs. And typically when you have that set up, you're going to want to run all of your complex calculations related to your network on the GPU. And meanwhile, your CPU should be doing other things. And typically that means handling your data. So that means opening files, reading the data, could be augmenting the data. Some people, it's very common when you're dealing with image data, for instance, to rotate the images so that your model is invariant to rotation. So that means that it learns that cats look the same if they're upside down or right side up. And then you package your data into a batch. Hopefully that batch term has become more familiar to you through the process of the tutorial. And then we ship that batch to the GPU because it has its separate memory space where it's going to read the data, compute on that data with the neural network, and do the backpropagation for the SGD process. So I wanted to talk a little bit about how we handle that, how we make smart choices when we build those workflows or those pipelines. Those are all just terms that we use to refer to the order of operations. So here I have a little visualization of what this might look like if you have a CPU and a GPU system, where on the CPU you're processing the data into a batch that you can then pass to the GPU to do all of the matrix calculations that are needed to process your neural network and the backpropagation, the gradients calculation. And in the most basic setup, this is what it might look like, where you process your data, you get your batch of data, you ship it to the GPU, you run the training once on that batch, and then you do it again, and then you do it again, and you do it again. Once you complete doing this for all of your data, you finish your epoch, and you're probably going to do it again for some number of epochs, right? Now, this works, but you can see while the GPU is making all of its heavy-duty calculations, the CPU is sitting here doing nothing, and vice versa. What we would like to do is to overlap this so that while the CPU or while the GPU is crunching the numbers, our CPU can be opening files, concatenating those into batches, and preparing to move those to the GPU to minimize the downtime here and shorten the time that we have to wait for our software to finish, for our training to complete. So it's coupled to efficiency, right? The other thing that we can do, another level of efficiency, is if we zoom in on what the CPU is doing to prepare our data. So some of this might be apparent to some of you who have experience, but I wanted to make sure we delve into this idea of concurrency. So modern CPUs, so 20 years ago when you bought a CPU, it had a single compute unit. When you run your software, it could only run one thing at a time. Sure, there might be hyper-threading and whatnot, but really you only had one thing that you could do calculations with. And so everything was serial. And when I say serial, I just means that everything was happening sequentially. First you had to do this, and next you could do that, and then you could do something else. In modern day processors, you have, on HPCs, you have typically 10 to 100 cores that you can deal with on a CPU. On your laptop, you even have, of order 10 cores that you have to work with. And so if I write my data pipeline on the CPU side such that I do it sequentially, right? So let's say we're dealing with images, you need to, you need to read that data from the image file that's on a hard drive somewhere. You're going to process that data somehow. Maybe you're going to scale it or rotate it or normalize it. And then you're going to map that data onto something that TensorFlow can use and that you can pass into your model to do your training. So that's one image. And now you got to do it again and again until you build up a batch of 128 or 256 images that composes your batch. Now, if you do it this way, that's fine. But again, you're not being very efficient because, like I said, most CPUs these days are multi-core. And that means that while you're doing this sequentially or serially, you've got a bunch of other cores that are sitting around doing nothing on your computer when they could be busy speeding up your activity. So ideally, you want to make this even more parallel where you break these functions apart. You have things like reading the data happening. So I read in a file. Core number 2 can then process the data from that file while core number 1 is reading in the next file. And so your images get processed diagonally here in this workflow, where you read in the data, the next core is processing that data, the next core is mapping the data to something in TensorFlow and adding it to your global batch, and so on and so forth. And now we can do quite a bit more faster because we're using our resources more efficiently. Okay, and so once we finish that, we can move our, worry about doing the move to the GPU after we've composed our single batch. So now I have an exercise here that I'm going to review. So we're going to review that here. And actually, maybe I'll go ahead and put this into Jupyter. So let's go ahead and log ourselves into Jupyter. So we're going to jupyter.alcf.anl.gov. And then we're going to log into Theta GPU. Okay. Use our mobile token. So this week, you really have to be using our ALCF Jupyter because we're going to be utilizing the data set that sits there, the same one that we used last week. Hopefully our access issues have been taken care of as far as people being able to read the data. It's now in the project space for the ALCF AITP project, which hopefully you're familiar with by now. Hopefully Jupyter Hub is working. Are there any issues going on with Jupyter Hub? Okay, there we go, good. So I'm going to select a Theta GPU compute node. I want the single GPU queue and the ALCF AITP project. And I'm just going to set this to 60 minutes. There we go. Or at least in the console, I can see that my job is now listed as running. Okay, good. I'm gonna have a quick look and see if any of you are trying to hop on as well. Good, I see a few people submitting jobs. Good, okay. So hopefully you got on the first try, unlike myself. So now I'm going to navigate to my directory. So I have to find the AI science training series in my home area. And then I'm going to go into the data pipelines, and I'm going to click on this exercise concurrency. So I wanted to talk a little bit about CPU side concurrency. And so I put this exercise in just because I didn't want to assume that everybody had been exposed to this yet. And I think it's a helpful concept to really spend a little time on. And so we'll have some breakout rooms. Hopefully that doesn't catch Paige by surprise here in a few minutes, but I wanted to go over this code real quick. So, first, of course, we load up the modules that we need. Let me make sure I have a reasonable kernel. I'm just going to take the usual conda with the latest date. Okay, I'm going to rerun this. These are all pretty standard modules, so they should all be installed. So, like I said, our pipelines are often made out of these pieces, right? So you read a file, process the data, and map it into a batch format that TensorFlow can utilize. So in this example, I do just that. I'm going to get my list of images. So all I do is I open up that JSON file to retrieve the training file list. So this is now a list of all the, or this is the file name that lists all the JPEGs from the ImageNet dataset that was used last week. I'm going to open that file list, and I'm going to loop over that file list. And I'm going to grab the top, and defaults to 100, but I'm going to be able to specify the number of images I want it to retrieve. And so it's going to return a list of JPEG file names for processing. So it's very similar to what we'll cover in the real data set. So now we process our image. So we have our image file name. We haven't actually loaded any of it. So we're going to open that file, read the JPEG data. We're going to resize it because the images come in various shapes and sizes, and we need them to all fit inside our first layer of our neural network, which has a fixed size. So we always need to resize our image. And often you would also do things like normalization. You might rotate it by 90 degrees or 180 degrees, however you like. We're not going to do that here in this example. This is just a short example with just Python threading. And then we're going to add it to our list of batched images. So we're going to create an array that's just a big list of all of the image data that we're going to use as our input. So this function does that for us. This is a little helper function where we pass in a single file name to our JPEG. So this tells us where on disk our JPEG lives. We want to tell it what's the shape of the images that we want to feed into our network. So it's going to be some shape that looks like this. And then we want the actual data object that will hold our full batch of data, right? So this is going to be an array where the first index is the number of images in a batch. And then we have the width and the height of our image and the number of channels, which is typically 3 for a color image. And then the index tells us which in this data, this output data, where are we going to save it? So which number are we in the batch? So this is just an integer. And so then we go through those steps. So the first thing we do is we open the JPEG, and we're going to use this, this pill module that is fairly common in image processing in Python. And it just has tools that are built for handling JPEG. So it knows how to handle the JPEG, open it, and then it has tools for altering the image. So in this case, it has a very simple resizing function. So all I have to do is tell it what was the past, what resize shape did we want? And it's going to reshape the image for us. And then I want to convert that pill image object into a NumPy array, which is something that TensorFlow could use to produce an actual TensorFlow array. And so at this point, I have a NumPy array that has a shape of the image. So it's the width, the height, and the 3 channels. The width and the height vary from image to image. That's why we're resizing. But the width and the height at this point is whatever this resize shape was passed as. So we'll define that as we call the function. I noticed when I was writing this that sometimes we load images and they have no channel number. So they're missing this, and that's because they're black and white. So they're monochromatic. They don't need 3 channels, they only need 1. And so to join these all together in the final batch data, I needed to artificially add additional index here so that the shapes of the arrays were the same. And so this is only operated on if the data shape only has a width and a height. So the shape is only 2 dimensions versus 3 dimensions. So, and then the final thing is in order to place our data into, which at this point, our data should be 3-dimensional. And you might recall that the batch data is 4-dimensional because it has an additional index at the front that tells you which image in the batch are you. And so we need to be able to copy that into the batch data, copy our image into the batch data. So what I'm doing here is simply changing from width, height, and 3 channels, is I'm adding an additional index here so that the number of dimensions in our array are equal to the number of dimensions in the batch data array. And so now I can just insert my image at index X, whatever it is. It might be 0, 1, 2, 3. If I have 24 images in a batch, it's going to be 0 to 23. One of my images will go in at that location, and the rest of the indices, we just want them all copied into place. Okay, so just to review, this process images opens our file, converts it to NumPy, reshapes it to be so that every image is the same size, has the same dimensions, and then puts it inside the batch data NumPy array, which we passed in, mind you. Okay. So we can do this serially, and we'll do that right now. So this piece of code, I guess I have to execute these to make them live. I think I executed this, and so I'll execute that. And then this. And so we can set our batch size. In this case, I'm just setting it to 1,000. And then we have our resize width and height. And then our resize height is just a tuple. When you use the parentheses, it's called a tuple in Python. And this is where I am retrieving some number of file names for the JPEGs. So I want my batch size worth of file names. So this is just a Python list of strings that tell me where to find the JPEGs. Now my new image is going to be the actual batch data. Should have renamed that batch data because that's what it corresponds to. Let's go there. And so when you do this, when you call this NumPy, NP is NumPy. So when you call into NumPy and you ask for an array that's filled with zeros. So this is just an empty array that I can overwrite later. And I'm going to create it with the size of the batch size as the first index, the resize width, the resize height, and I want 3 channels because these are color images, most of them. And so this is just going to create a 4-dimensional array that's set to 0 everywhere. And now I can loop over the image files. So remember, these are the file names. So I'm just looping over the file names. For each file name, I'm going to pass in the actual single file name, the resize shape, the batch data, and the index. So this I is just going to be counting up from 0 as it loops over the image files. And I'm timing that as well. So I have a start time and an end time, and I'm going to calculate the duration, which gives me some measurement of how long it takes in seconds. And if I run that, you can see it took 3.14 seconds to process 1,000 images and put them all together in this batch data. So it processed 300 images per second, okay? So this is written serially, right? This for loop is happening over and over and over again. It's sequential. This is all using a single compute core on whatever single GPU node that I'm running on, okay? Now, like I said, our systems usually have multiple cores, and we can actually use Python to tell us how many cores. Okay, so the current system I'm on has 256 cores on it. This is probably actually the number of threads, hyperthreads, not the actual physical cores, if you care about such things. But no worries if that doesn't make sense. The point is that in principle, the computer that I'm on can handle 256 parallel operations. So I've measured how long it takes to process 1,000 images serially. It takes over 3 seconds. Now we're going to use threads, a threading pool, actually, to launch these images being processed in parallel so that every core gets its own image to process independent from one another. So that's what this piece here does, and we're going to focus right here for just a moment. I try and add some explanatory text here in the code, but we're using this thread pool executor, which takes an argument called max workers. So this is the maximum number of parallel threads that it's going to launch. It may be less, it may be up to the max based on how much work we give it. And so it's going to create this thing and it's going to save it into executor, and then we can use that executor to do things. So once we've created it with this with functionality, this is a Python construct if you're not familiar. Now I can use executor within this with statement, and that executor comes with a map function. Map allows you to tell it to, so we have that process image function way up here at the top, which processes a single image. I'm telling it, run this function once per thread over all the image files. So that function is going to receive one of my image files. It's going to receive the resize shape, the new image, or the batch image shape, which I need, anyway, the naming needs to be fixed. And then it's going to receive the number it's going to receive an index between 0 and the length of my number of image files. And you remember that in process image, I need the file name, the resize shape, the batch data, and an index. Okay. So that's what it's going to do. It's going to launch some number of threads. And if the number of image files here is more than the number of threads, it's just going to keep passing that data into those threads. So in this case, I set the number of threads to 2, and the batch size is 1,000. So I have 1,000 images I want to process, but I only have 2 threads. And I'm making this artificially small just for example. So I'm going to have 2 threads, and they're just going to keep working on 2 images each until this image list is empty. Okay, so I'm going to run this code, and hopefully it runs shorter than 3 seconds, which it does. And so you can see by using 2 threads, I've halved my runtime, have halved the time it took me to process these. If I change this number of threads to 4, I reduce it again. And actually, I think that's about as fast as it gets. At some point, there's an overhead. It went down again to 0.4 seconds. And I can go to 16. In principle, I can go all the way up to 256 without much impact in performance, but really I'm starting to run out of work. So I would want to up this number to, 3,000. I'll set that to 128. And that might take, see, that really bumps up the images per second. Okay. And I was able to process 3,000 images in less time than it took this serial job to process 1,000. So the exercise is to get into your groups. So we got about 10 minutes before the break. I want you to go into your groups. I want you to play with the number of threads. Sorry. I want you to play with the number of threads. You could play with the batch size too if you like, and get a feeling for the duration, the images per second. You might want to take some notes. In your notebook, you can add I want a markdown section. So you could add some notes like run 1 with num threads equal 5 and batch size equal 1,000, and then note the events per second for that, and then just continue how many, and just get a feeling for how this what we call scales. How does the process scale with the number of cores that you throw at it? Is it linear? So if you were to plot the duration with versus the number of total threads, if I double the number of threads and the throughput or duration doubles, then it's scaling linearly, is what we say, because you're getting the same number, you're getting the same bump. So I don't know, Paige or...
Yes, I'm prepared to launch in a breakout room. So I think 10 minutes. So we'll send folks into breakout rooms for 10 minutes, then bring them back for a minute, and then we'll go to break. Does that sound good?
Sounds good.
Okay, super. Well, then I will launch folks into breakout rooms. All right, welcome back, everyone. Hopefully you had productive conversations during your breakouts. I don't know if anybody wants to share in the Slack any of the things that they found while they were playing around with the code, or unmute if you will.
Yeah, I can say briefly what we found.
Yeah,
Um,
thanks.
yeah, so our group, we noticed that when we would go to the maximum number of threads, 256, it actually got less efficient. It took it a little bit longer time, and then the images per second got a little bit lower than when we were using 128 threads. So that was something that was interesting.
Thank you for sharing. Anybody else? I see Thomas in Slack posted a graph, which is wonderful.
We heard about strong scaling and weak scaling, where you can just increase the number of threads in one case, and in another case you can increase both number of threads and batch size proportionately. That gives you a different measure of the scaling.
Yeah, if you run out of work, right, then you kind of are limited by that. So as you go to more threads, you definitely want to increase in this case, the batch size, which is kind of an artificial word for just the number of images that you're processing in this parallel situation. But yeah, it was a good observation that going to the full 256 doesn't necessarily give you the best performance. And that's typically because we're moving into the range where you're using hyperthreads instead of physical cores. So typically, on a CPU, you've got actual cores, which means computational hardware that can do computation. And then there's this thing called hyperthreads, where each core can handle 2 to 4 parallel threads, where if one of your threads needs to pause and go fetch some data, but another thread has a computation that needs to be done, it can schedule those things in a way that makes it feel like there are 4 cores when actually there's just one. So if you don't have that, and it's really needs the processor, then you don't benefit from from using those hyperthreads. So usually it is common to see that kind of plateau above the number of physical cores, which in this case is probably 128 is my guess. I haven't looked it up. But anyways, so very nice.
Yeah, excellent. Okay, well, we will come back in 8 minutes at 4 p.m. Central and hear from Ricardo. So see you all in a bit. All right, welcome back. So as is tradition, we're going to now have a science talk from Ricardo Balin, who is a postdoc here at the Argonne Leadership Computing Facility. So Ricardo, if you want to go ahead and share your screen, you can get started.
Can you see the slides?
Yeah, looks great.
Awesome, thanks. Hi everyone, and thanks for the opportunity to discuss my work. In these 10 minutes, I wanted to give an overview of basically the goals of the project that I've been working on here at Argonne and what we're trying to do with machine learning. So the talk is called Online Machine Learning for Exascale CFD. So here the application is computational fluid dynamics, and the goal is to do machine learning and CFD together, and that's what online means. So the overview is pretty simple. I'll give an introduction of the project, and then a quick high-level view of what the workflow looks like to do online machine learning. Then just a slide on performance, since we are trying to apply this at scale. And then a few other mention of what we're doing on top of the primary goal. So what we're doing with simulation and machine learning together, and with some conclusions. So this is just a quick introduction about computational fluid dynamics, and specifically computations of turbulent flow. There's 4 main approaches. The main one that you might have heard of on the left is called direct numerical simulation. Here, The idea is that we're solving the unsteady Navier-Stokes equations directly. We are resolving with our grid all spatial and temporal scales of turbulence, so there's no modeling involved. It's the most accurate because of this reason, but it's also the most computationally expensive. Here in the middle is sort of the other edge of the spectrum, which is called Reynolds average Navier-Stokes, or RANS. And here we solve for the steady mean flow equations directly. Because of that, we model all of the turbulence scales, both in space and time. It's the least computationally expensive, but it's also tends to be inaccurate for some of the complicated flows that I'll mention in a second. So there's some compromise approaches here that are called large eddy simulation or hybrid runs LES or wall-modeled large eddy simulation. And here we are solving for the unsteady filtered Navier-Stokes equations. And the filtering allows us to resolve some of the largest turbulence scales and model the smallest. So it's a compromise between resolution and modeling. And because of that, it also gives us a compromise in terms of accuracy and computational expense. So our project is focusing on these large eddy simulation types of approaches for turbulent flow computations. And we're trying to develop closure models for large eddy simulation using machine learning approaches. And a closure model is really just a model for the unclosed term in the equation. So we have the filtered Navier-Stokes equations. Those are our governing equation. The filtering operation produces some terms that there's no closed form to express that term. And so we have to introduce a model. And that's what we mean by closure models. If you are trying to develop a neural net model for LES and something like wall-modeled LES, there's a sort of an important detail, and that is that we need to train the model on instantaneous flow data. And so, as you can imagine, as our simulations become larger and larger, as we go to exascale simulations, this means that we have very, very large amounts of data. We actually have, we would need multi-terabyte databases to store all of the training data that we would need to then train our model. And so a way to avoid this input-output or storage bottleneck is to do machine learning in situ or online. So this way we never save our training data to the disk, and we are storing it in memory throughout the duration of the job. And this allows us to concurrently run the simulation that produces the training data, as well as the machine learning that uses that data to train a model. So you might ask, why do we need to train on the entire flow domain? So why do we need this much data? And the answer is because there is, in realistic applications, a lot of different physical disturbances that change the character of the physics. And so a predictive model must be accurate on all these physical effects. And for something like the flow over a bump, the turbulent flow over a bump, as you can see in this picture, it doesn't really matter what these physical effects are, but I just wanted to go through and sort of point out how many different effects there are just in this simpler flow that change the character of the turbulence. And so we need to train the model on the entire domain. Another question that might arise is, why do we need to train on multiple snapshots? So why can't we just save a single snapshot of this flow and then train the model on that? So this would only require one snapshot, which is not that much data. It's a couple terabytes, but that's doable in certain scenarios. And that's because often a single snapshot does not contain all the time-dependent phenomena that the model then needs to be able to handle during inference. So when we run, for example, a large eddy simulation, that will be time evolving. And so we need to have contained all the time-dependent phenomena during the training data as well, during training as well. And also some flows of interest are actually not statistically stationary. So that means that the flow and the mean of the flow actually evolves during time. So that could be, some examples are the internal combustion engine. You have very distinct phases where the flow looks very different in those phases. An active flow control application that I'll actually show in the next slide. Or for example, a wind turbine under variable wind conditions during wind gusts. You need to sort of the response of the wind turbine to the gust is a time-dependent process. And so you would have to include that time-dependent process as part of your training data. So as I mentioned, bumps are insightful, but really we're trying to tackle some more realistic cases. An example of that is shown here. We're really trying to do full computational fluid dynamic simulations of complex aeronautical and aerospace systems. This is, for example, the flow over a vertical tail of an aircraft. And on top of that, as if wasn't complicated enough, as you can see here from all sort of the turbulence scales, we have a synthetic jet here on the surface. You see the zoomed in picture on the right, that's pulsating air in and out. And that is introducing even more complexity. And so these are really the cases that we're trying to apply our models to, and training on a bump, trying to reproduce the physics that we'll then see in something like this. So then we can have predictive models for these types of simulations. At a very high level, we have 4 components to our workflow. There is a simulation, a machine learning component, an in-memory database that will store our training data and some other parameters, and then a data transporter. So sort of a high-level overview or schematic of the workflow is shown here. And we are leveraging an open source tool called SmartSim and SmartRedis. They go hand in hand. And this really allows us to deploy the database. And then also it gives us APIs that allow us to communicate from the simulation to the database and vice versa, and same from the machine learning component to the database. So you can see here for training, we have the simulation connecting to the database, which is also connecting to, in this case, it would be distributed training to be able to do training in parallel concurrently with the simulation. In the case of inference, we can do the machine learning component here is inference. We're evaluating the model, and we can do this directly within the database. So we get rid of one extra connection to the database here. Now, we've been able to demonstrate that for an implementation of this that is actually called co-located, the details of it are not necessarily important for this talk. But I wanted to point out that this is indeed scalable. So if you see at this blue curve here at the bottom, what we're showing is the communication time that is required during online inference. So during inference, the CFD solver is sending inference data to the database, evaluating the model, and then getting predictions back. And this has to be done at every time step, again, to do inference and close those governing equations with the neural net model that we just trained. And you can see with the co-located approach that as we increase the number of nodes, here we go to about half of the size of Polaris, that overhead time actually stays constant. So that means that the cost of scaling this workflow really just depends on the simulation and the data parallel training in the case of training. So basically the workflow doesn't add any issues with scaling. And beyond turbulent closure modeling, we're thinking about a couple other things. One example, or the most straightforward, is basically to just be able to train multiple models for turbulence at once from also multiple simulations. So there's really no limit on how many simulations we can have connected to the database, and also how many sort of machine learning components we can have connected to the database. So you can imagine we have, say, multiple bumps or different geometries feeding simulation data for training, and then we can train multiple models, even to do different things. For example, closure, we can have a compression model, and we're also looking at some turbulence generators as well. Or you could have multiple instances of the same model doing something like a hyperparameter sweep. Another thing that we're looking into is adding user interactivity to this online workflow. What this means is that we're really trying to add a way for the user to be able to manipulate the data and the training as this is ongoing on the machine. So we could have a user dedicated node where the user can sort of interactively code and run scripts or notebooks interacting with the database. So for example, you could plot and visualize training curves. You could validate model checkpoints on validation data that you could bring and upload to the database, which is not provided by your simulation. Or you could change some hyperparameters on the fly if you wanted to. And another thing we're considering is adding online or in situ, again, visualization with something like ParaView. So this would allow us to not only see the progress of our simulation, but also visualize some of these complicated flow fields that you saw in the previous slides, and see how our model is predicting some of these quantities on the entire domain. So we produced some of the pictures you saw earlier that were actually done with ParaView. So to conclude, the goal of our project was to develop a software infrastructure that was able to combine CFD with online machine learning at scale. And we've so far used this to perform online training and inference of neural net models. We show that an implementation of this workflow is actually very efficient and very scalable. And we are currently using it to develop so-called turbulence closure models for aerospace flows, but it's easily extendable to other applications, not just within turbulence and CFD, but also to other physical and computational domains. So that's all I had for today, and this is an overview of our project. So I'm happy to take any questions and discuss any other topics that may arise.
Thank you, Ricardo. So we have one question in Slack already from Mukul. Mukul asks, can you give an example for what closure variable could be trained? So Mukul gave an example of like a subgrid kinetic energy.
So something we're looking at specifically for LES, it's called the subgrid stress tensor. So it's basically, if you're familiar with RANs, you do a Reynolds decomposition. You take the filtered product of the velocity and subtract that to the product of the filtered velocity. And that is the unclosed term. But you could do something with kinetic energy as well. You could do basically whatever traditional models have done so far. We are trying to right now replace a traditional sort of algebraic or differential equation that represents that unclosed term with something like a neural net model.
Thank you. Okay, another question. Ping Xuan asked, when you use machine learning for the closure model, do you have to run DNS to get the data?
Yes, that is sort of the first step. But it truly depends on what fidelity is high enough so that you trust your training data. And if you're doing LES, which is sort of a step below DNS, then you sort of need the higher fidelity approach to turbulence computation to produce that data that you need. But you could imagine instead, if you're trying to develop a wall model for LES, you could use just regular LES and focus on the near wall region to develop a wall model. So basically, I would say it really just depends on what you trust is accurate enough to compute the training data you need.
So at the end of your talk, you mentioned sort of potentially being able to apply this to more models. Are there models that you have specifically in mind, or that like potentially scientists in other fields could use this model to help understand their systems better?
So the first thing that we're considering other than the closure is compression. So the idea here is to use something like an autoencoder to compress. This would be just the simple fields, velocity, pressures, and temperature, preserving though the quantities of interest. And this would be something that could be extendable to, for example, climate computations as well. You know, the atmosphere is turbulent. And so something trained on a turbulent flow or designed for something like an aerospace application, like we talked here, could perhaps just require small adaptations to be applied to something like climate modeling or wind turbine modeling, things like that. Same with turbulence generators. Here, the goal is to just represent turbulent fluctuations, for example, velocity, pressure, and temperature. So again, this could be extrapolated to something like climate modeling or other types of flow computations. But in general, sort of the setup and the workflow we think is very general and can help any computational field that requires some sort of model, whether that's closure modeling or a surrogate model where you're trying to represent some part of the simulation that is either expensive or inaccurate. And basically the training data, the simulation producing the training data would benefit from this online infrastructure.
Awesome. Okay. Well, I think we're close to end of time. Does anybody else have any other questions? Feel free to drop in the chat or unmute. All right. If anything else comes up in Slack, obviously you're welcome to respond directly to folks there. But with that, thank you so much for coming and presenting today, Ricardo.
No problem. Thank you.
All right. So we shift back to Taylor now to finish things up with data handling. Taylor.
Thank you. So hopefully the exercise we did before the break was a bit helpful in giving people the idea that concurrency is helpful and a little bit more intuition about how to use it when we talk about it. So next we'll talk about the actual data pipeline that we built for last week's example. This is using the ImageNet data set. So here are a couple of examples of the images that you'll find in the data set. As I said before, the shapes and sizes vary because these are JPEGs taken from the real world. In principle, the data set contains examples of 1,000 different class objects or labeled objects. And with those come a set of XML files. Those XML files, if you're not familiar, they tend to look like this, and they contain information about the image, the shape of the image. They include information about the objects contained in the image. In this case, the object ID is this long string of values. And then it also provides BND box, which stands for bounding box. So it's a box that bounds the class object that's being labeled. And it gives you the X-min, Y-min, so it gives you two corners, right? So that you can draw a square based on those corners at right angles. So you can imagine the bounding box being something that bounds this dog, so it tells you where in the image. And so we are going to build a data pipeline that reads in the JPEG. The XML files share the same name, but with different a different path and a different postfix. So instead of .jpeg, they're .xml. So we will provide a list of these images. We will convert that path into the XML path so that we can open both files. We're going to parse this XML file using the built-in tools from Python in order to read in this bounding box and the class information. Although I guess actually I take the class information from the file name because it's the same. And then we will slice the image based on the bounding box. So we will take only the pixels that fall within the bounding box and use that as a single image. The ResNet example that he provided, that Corey provided last week, does a single image, single classification. So you don't want lots of objects in the same image. So that's why we use these bounding boxes to cleanly cut out the class object. So we're going to, sticking with TensorFlow, although you can it's pretty straightforward to port this to PyTorch. They have a similar data API. I would say the TensorFlow data API is a little better at being parallelized, a little easier do that with than the PyTorch, but in any case. And so let's get started. We're going to look at the training file. I'll bring that up in just a moment, but I've got a few pieces highlighted here that I thought would be useful to look at before they're surrounded by code. So like I said, we're gonna start with a file list, or a file that contains a file list, right? So we have imagine a text file, and on every line of text, it's a full path and file name for a JPEG image. So we're gonna open that file. We're gonna loop over the lines in that file and fill up a Python list with those file paths. So now we have a Python list of those files, but we need to parse that into TensorFlow compatible formats. And TensorFlow has a data API. It's tf.data, and then dataset is a class within that API. And that class has a static function that allows you to just pass it a Python object like a list, and it will convert that list into a TensorFlow tensor. So when I pass this list of strings, it's going to create a TensorFlow tensor of strings. So I still have just the file names. Now, next week, we're really going to start digging into how to parallelize your training on multiple nodes with MPI, because this is, of course, about supercomputing, right? We've been working on single GPUs for the whole class. Next week, Huiho is going to introduce Horavat, which is a special tool that implements the MPI pieces that allow us to run our training across multiple processes on different compute nodes. And when we do that, we're going to need to use a tool called sharding your data. Shard seems to be the settled on term for what this means, but because you'll see this term in both TensorFlow and PyTorch, which is nice because at least it's uniform. Sharding really just means that if I run my model on 2 GPUs and I have the same model on both GPUs, if I load up the exact same data and train both of those models, I'm going to get the exact same result, but that's not very useful because I have 2 GPUs. Why am I using 2 GPUs? Really what I want is to create a batch, give it to one GPU, create another batch, give it to the next GPU, and so on and so forth. I want each GPU to see different pieces of my data so that I can go through my data twice as fast with 2 GPUs. So by sharding my data, I have to tell it how many, the technical term here, MPI ranks, how many processes, parallel processes am I running, and which of those processes am I? So if I have 2 processes, this value is going to be either 0 or 1. And that way, TensorFlow will keep track and it will say, well, rank 0 or process number 0 is going to only see these data, and process 1 will see this completely different part of the data set. And through the 2 of them, they will see all of the data set. And if you have 10, it's going to divide it up by 10, and each process will process different data, and it will go 10 times as fast, quote unquote. Not quite 10 times, it's not linear usually, but it's near linear typically. So I introduced that here. We're not going to dive into that. That will be next week. The next step is to shuffle our data. So we've applied the shard to the file list. We're going to shuffle our file list so that at each time we pass through our data, we want to randomize how we put that data together into batches. If you don't randomize your data, your model can fail by learning the order that your data comes in instead of the actual features that you care about. So you do want to shuffle your data as you train. So that's what this does. There's something called the shuffle buffer in the config file, and that just tells it how many images to load up, or how many entries of this thing, which in this case we're talking about file names, to load in and then randomize their organized order. Okay. I think this is set to like 20,000 or something. So it's much bigger than the batch size typically is what you want. And then we have, so notice each time I call this, right? So I created the initial tensor, and the tensor has these functions that I can call on it. And when I call it, it generates a new tensor, which I use to overwrite the old one essentially. Okay. So that's the behavior you're seeing here. So I'm shuffling it, and then I'm returning it to the same thing. In reality, it's creating a new one and then replacing the reference with the old one. So next, so you remember up to this point, I've got just a list of strings. So at this point, I'm going to call this mapping function, which is going to call, this is a Python function, load image, and the label bounding boxes. So at this point, this function is going to open the JPEG image, load up the JPEG, turn it into a tensor, resize it, join it into a batch, all that stuff. It's also going to open up an XML file, parse the XML, find the bounding box, chop up the images if need be. Okay. Now with this mapping function, there's a parameter of the function called num_parallel calls. And so this allows TensorFlow, if this is independent, right, if it can be done on the data independently, and it can because these are just lists of file names, it can do it in parallel. So we're going to tell TensorFlow, we want you to call this function some number of times in parallel. Here in this text, I introduced this auto tune. So TensorFlow has the ability to try and learn this function on its, or this number on its own. Usually it's probably based around the total number of CPU cores you have. And in the actual code that we're going to look at, I actually physically control this to give you control over that. And so at this point, now my data set's starting to look like a data set, because now it's actually images, labels, right? It's got the inputs and the truth information that we need to calculate our loss. Now, this load image can sometimes return multiple images per file because there might be 2 dogs in the picture, and it's going to cut those out based on the bounding box and return them both. And that's what this unbatching function does. So it's going to unbatch those as necessary. And then finally, I'm going to tell it I want some batch size for the actual training. So this is where it's going to create the actual training batch. TensorFlow also provides this prefetching function for data sets. Prefetching essentially is what happens here to here, right? If you do not prefetch your batch, you're going to do it serially with the GPU. So you'll build your batch, you'll send the GPU its data, and then it's going to ask for the next data set, and you're going to batch it, send it, and it's linear. If we prefetch, the data API is going to say, okay, I've sent my batch, I can start preparing the next one. And I've been told to prefetch n numbers of batches. So if I have enough time, I'm actually going to prepare the next batch, right? So it's going to go on ahead of the call and start building the next batch, even though it hasn't been asked for yet. So that's what this prefetch call. And again, in this text here, I use the auto tune. In the actual code that we're going to look at, this is a tunable parameter. So you can tell it how many batches to prefetch. Okay. The same submit calls are here. Oh, I need to fix these image links, but I will be showing you those live anyway. So I'll fix those later. So you should recognize this code from last week. I've made a few adjustments to control the parallelism. So at the top, I've added some control knobs for us, number of parallel threads, the prefetch buffer size, and then I set this OpenMP num threads, which controls some other parts of TensorFlow. TensorFlow is pretty, I would say smart, but it's on the edge of too smart, whereas it's very convoluted to try and control how many threads TensorFlow wants to use in these APIs, such that I had to bend over backwards to try and force it to only use one, because I wanted you guys to see the effects of serial performance. So the other thing is I've added the TensorFlow profiler, and we'll see the output of that. And since the TensorFlow profiler is memory heavy and the memory grows with the number of training loops it executes, I've set the training loop up to stop after some number of steps so that we don't just segfault because we've run out of memory. So whenever we use the profiler, it's going to stop after 10 training steps. Otherwise, things are very similar to last time. You can see in the training loop where I've added these. So this is the train epoch function. This is the profiler call, so starting the profiler. I've added some things for calculations here for the average image rate. And then at the end, we want to stop our profiler, and I also print out the mean image rate and standard deviation for your information. Let me see if I can bring up a quick example of that running. What that looks like before I jump into, okay, there we go. So if you are on a compute node, so in this case, I created an interactive session. So I did a qsub command on the command line, which maybe we'll just walk through that real quick. So here I am logged in to Theta. I need to make sure that I have module loaded, the Cobalt for Theta GPU. Okay, so I should be able to see you guys running jobs. I see some yep, good. See some people with their single node jobs. If you're in Jupyter, you're going to want to switch now to the command line. So you want to close down your Jupyter notebooks. You can do qstat-u and look for your username. I don't have any jobs running, so I'm not listed. So then I'm going to run qsub-i, which makes it an interactive session. I'm going to do ALCF, AITP. I want one node. I'll do 30 minutes. And so that's going to start up an interactive job on a single GPU node. And it's going to drop me in my home directory. So I'm going to want to go back into We might be full. Which would be good. That means you guys are actually using the allocation. Let me try. Let's see if that gets me in a little faster. Oops, I spelled sing. Go GPU. Oh, of course, this is not going to let me in. What's going on? Maybe that we're running up against the reservation. Which may end at 5. Is that what's going on?
Did you load the Cobalt GPU?
I did.
Okay.
That's what I get for trying to do something different. It may just be full. Yep, it might just be full. Okay, I'm going to go full node because I do see an empty full node. Let's So when you're playing around with this on your homework, which is going to be very similar to the exercise that we did at the break, but with the actual data flow. So I'm going to have you play around with these values. Okay, that's working. What I will have you do, you can do this interactive session and then go to your notebook, go to the data pipelines, and then if you follow or just cut and paste the module loading from the train ResNet 34 data GPU, we need to load up our environment, our Python environment. So we're going to get our Conda module, we're going to activate it. So now I can run Python with all the TensorFlow stuff. And then I can run Python train. And so this will actually run the training. Okay. This always takes a little bit to start up. So in general for this, you only need the single GPU. And once our reservation is done, there should be enough available for people to use. And that's because we only need one GPU in this case. Whereas if you do a full node, you're occupying 8 GPUs. So you're kind of wasting resources. So try not to do that. Here we go. So in this case, I have my threads set up to use 128 threads. You can see the batch size is set to 256. Here's the model getting printed. We're starting the profiler. We've got our ResNet 34. And we'll start looping over the images. So it's set up to run for 10 iterations, and then it will give you a summary of these values. Okay, and now let's dive into the code. So I'm going to switch back Chrome. Okay, so now let's go. So the dataset API is implemented in this file here, the ILSVRC, which is some weird acronym from the ImageNet folks. And so if we start with the get datasets function. See if I can make this bigger. This is really just reading in that JSON config file and reading in some of the configuration information. It's getting the paths to those file lists, right? So these are those file lists that I described in the README. Make sure that those files are actually existing. And then this function I won't cover, but it essentially maps those weird class ID numbers onto a list from 0 to 999, because we have 1,000 classes. This just makes it orderly and also makes it actually usable for a machine learning model, which isn't going to spit out this. It's going to spit out something more like this. And then I have a separate call for the training and the validation data sets. So we have this build data sets from the file list. So it takes the configuration and then one of the file lists. So we will start here. So here we are just we're loading in those actual files. So now I have a Python list with a bunch of strings that tell me where those files are located. Here I'm converting those into a tensor. If Horovod is being used, I'm going to shard my data based on the number of parallel processes and which process am I. Shuffle my data, run this map that maps the file name to an actual image and a label. And then I'm going to unbatch if there were multiple images returned, and then I'm going to rebatch per the configuration batch size. And then I'm going to prefetch some number of batches to be efficient. So let's just look quickly at this load image label and bounding box function. So this is taking the file path to the JPEG and replacing some things to make it point at the XML file. And so once I have that annotation, that's the name of the files, these are annotation XML files. Once I have that file name, I can pass it to this get bounding box function. And that is going to return the bounding boxes and the number of boxes. And I'm going to use that later to chop out sub-images if there are more than one class in my JPEG. TensorFlow provides a tool for reading JPEG. So I have the image pass that was given to me was a JPEG. I can read that directly using this TensorFlow IO read file. So now I have my JPEG image data. I can convert that image data into an actual tensor. I have to tell it how many channels the image is. And so it's going to convert that JPEG into just a plain old TensorFlow tensor, which is like an array. I'm going to add that batch dimension in the beginning. So that's going to be the 0th dimension. So I'm expanding my image from being just width, height, channel, adding the batch. You might remember that. And then TensorFlow provides this crop and resize function, which takes the image, takes the bounding box information, and then I tell it what my crop size is going to be. That comes from the configuration file. And so this is looking at my image. It's going to chop out each of these bounding boxes, resize it to the shape I want, and then return it as a new tensor. So this is literally going into, if I had 2 dogs, it would take the bounding box, which shows me which dog is which, and it's going to chop out an image based on that bounding box and create 2 images from this one, and they have the same class. Here I'm just doing some data typing. It's read in as an integer. As the integers, I'm converting it to floating point for my model, because all the math is in floating point. I reshape these just in case, and then I grab, I've got their label from the file name, and I'm going to map that label, which is that N0 some number, and I'm going to map it to the 0 to 999. And so now I'm returning whatever images were extracted from the JPEG and whatever labels correspond to those images. It might be 1 image and 1 label. It might be 2 images and 2 labels. Okay. And then the nice thing is, so I have to do the unbatch because I may end up with multiple images. But the nice thing in general is that TensorFlow builds the batches for you. Using this batch call on the data set. So now I've created my data set. I can run this with parallel workers. I'm going to change and spend the last 10 minutes in this Firefox window, which is running the TensorFlow profiler viewer TensorBoard. It's called TensorBoard. So when you run your profiler, it's going to drop some data in the file folder there. And this viewer can serve up that data in useful ways. So if I run the training and I tell it at the top, I'm going to use, actually, I need to show that so that it's clear. So we're going to go back to the training file. So train resnet 3.4. So this is my version. Well, my edited version of Corey's from last week. So the 2 parameters I'm going to be playing with are the parallel threads and the prefetch buffer size. Okay. So parallel threads, prefetch buffer size. Remember that. So remember that the parallel threads tells TensorFlow how many parallel threads it can run to create batch images. And then the prefetch tells it how many batches it can load up in advance as a just in case. So now if I run that and I set the number of parallel threads to 1, okay. Let's see, I'm gonna make this smaller because I don't think I can make any of these things bigger, any of the text. So if I make my window smaller, I think your zoom will get bigger. So what you see in this view are 2 devices separated by these solid gray lines. This is the GPU and this is the CPU. Time is up here on the top You see 10 seconds, 20 seconds, 30 seconds. This is our runtime. So you can see if I start at 0, the single threaded job ran for about 50 or so seconds and performed 1, 2, 3, 4, 5, 6 training steps. Okay, now I can zoom in here. Now, interestingly, what you'll see in TensorFlow is what's happening is the data loading is all happening on the CPU. The the machine learning computations are happening on the GPU, and you can see that immediately when it starts up, it starts loading data, and then it calls the first training loop, which triggers actually a just-in-time compilation. So the first training loop is always really long, so don't consider timing when you're don't include the first training loop in your timing, is the lesson there. And if I zoom in here, we'll see, so you can see the data reader, which is here. So this is my single thread, which is loading 256 images. And then it says, okay, here, GPU, here's my 256 images, do your computation. So the computation takes, 200 milliseconds, while the batch creation took 5 seconds. So we are really limited by how quickly we can form our batches. So now if I move to 2 threads, so now I'm in 2 threads. Let me zoom out here. So here again, you can see, and now you can see I have 2 threads here, which are reading in data. And you can see, let's see, we were at what, 5 seconds before, now we're at, half that roughly, 2.5 to 3 seconds. Okay, but you can see now we've got 2 threads running. Now I'll go to my 4, so I increased it to 4 threads. Okay, so you can see my reader threads down here. Shrink this. Okay, then I'll zoom in over here. You can see, again, load up all of our data. Now we're under the 2 seconds. So it looks like about a 1.5 seconds to load up our data, or at least one batch of our data. And I'm going to zoom in here because I want you guys to see what's going on, and I need to expand one of these threads. So in this profiler, you can see the activity of the data reading. So you can see the read file. So this is the JPEG. You can see, like, if I zoom in really far, there's the deep code JPEG. Here's the crop and resize. It's being casted. There's another resize being called. You can see the get bounding boxes call, which takes a long time. So you can zoom in here and you can see all those activities that the thread is doing, that the thread is performing. So we have 4 of them there. We're going to jump to 8. We'll do, again, you can see 8 threads there. 1, 2, 3, 4, 5, 6, 7, 8. And you can see it over there. So, I mean, we've gone from a total runtime, let's see, of about 50 seconds. At 8 threads, we're at 22 seconds. So I'm just going to keep going here because I'm almost out of time. And we'll go all the way up to There we go. This is 128. So 128 threads. And you can see them all down here. Them all down there. They're all running in parallel. They're really thin now because each thread is not having to do very much to get to 256. So if I zoom in on my steps, now you can see the computation on the GPU side. You can see the data preparation down here below. All those greens are reading JPEGs, okay? And all the purples are essentially reading XML files. The actual loading of the data from a file system that's connected via a network is the slowest piece right here. But you can see we're not overlapping at all, right? There's data pipeline and there's GPU calculation. The GPU isn't doing anything while we're loading data, and the CPU isn't doing anything while we're computing the batch of data through the model. So if I change the number of prefetch, so that's with prefetch set to 0. If I just increase that to 1, it takes a moment to load. And so this is going to be your homework, is to play with the thread values and the prefetch values. And again, if feel free to make a plot. Feel free to make a table if you're not comfortable with making plots. So you just vary them, run the code, and keep track of the mean image per second and the standard deviation. So if I increase, if I tell it prefetch 1 batch, you can see now we have computation and reading going on at the same time. So you can see the computation here on the GPU, and I need to make my window a little bigger, but you can see during the GPU, there's activity down here. Not much, but there's some. But if I increase the prefetch to 8, let's tell TensorFlow, I want you to prefetch up to 8 batches of data while the GPU is doing its computation. We can really fill up our GPU or our CPU with activity. Keep it busy and max out that image throughput. Okay, so this is with 8. And I just want you to see that where the GPU calculation is taking place, which is over here, you can see that the CPU, so here's, GPU activity in these bands right here. This is all memory copying the batches to and from. This is the actual computation in these colored bands. You can see the CPU is just always busy then. Every thread is just constantly loading. There are a few places where it decides to pause. But for the most part, once you hit this max out, what you're going to find is essentially we are busy reading the XML files or the image files. And so we've become what they would call as IO limited. We need to work on how we store our images. And the next step of optimizing this workflow would look like, instead of doing all this processing on the CPU all the time, just process the data once into some larger file and then reduce the amount of this individual reading that we're doing. Okay, so that is pretty much it. I want to come back and close here. And it's in the README file, but the point is I want you to grab a single node. If you can, doing it interactively is easiest, because then you can just rerun the Python command once you have your Conda environment set up. Vary these numbers here and here. Make a plot if you want, or tabulate it, and submit those as your homework. And the idea is just to see how the parallelism affects your ability to reach your solution faster, which is very important in HPC or in supercomputing.
Awesome. And I assume, Taylor, for those that I think had to drop off a little bit early, you'll put that information for what is homework in the Slack as well. So
the homework is on the
perfect.
README of the, yeah.
Okay, we'll point to that just in case as well. All right, wonderful. Well, thank you all for coming. See you next week and have a good week.